You were taught that a planet orbits a star. The official definition of a planet, written in 2006, says it must orbit the Sun. That single sentence erased billions of worlds. But it did not erase them from the universe. It only erased them from our count. On August 24, 2006, in a crowded hall in Prague, the International Astronomical Union voted. They had gathered for their 26th General Assembly to answer a question that sounds simple. What is a planet? The text they ratified has echoed through classrooms ever since. A planet must satisfy three conditions. It must orbit the Sun. It must be massive enough for its own gravity to pull it into a nearly round shape. It must have cleared its orbital neighborhood of other debris. The third clause killed Pluto. The first clause, orbit the Sun, quietly erased an entire category of objects no one in that room had yet confirmed existed. The vote was 237 in favor, 157 against, with 17 abstentions. Barely 4% of the IAU's nearly 10,000 members cast a ballot. The definition was drafted by a committee, debated for days, and passed in the final hours of the assembly. Many astronomers walked out. Some called it a hurried compromise. Others noted that the resolution defined planets only for our solar system and explicitly declined to address the hundreds of exoplanets already being discovered around other stars. The word star does not appear in the definition. Only the Sun. A planet, by the language ratified that day, is a body that orbits a single specific star, ours. At the time, the omission seemed harmless. Every planet anyone had ever seen orbited a star. Mercury through Neptune, each traced a path around the Sun. Every exoplanet detected since 1995, 51 Pegasi b, and then a cascade of others, orbited its own parent star. The link between planet and star was so complete in human experience that it had collapsed into identity. To be a planet was to orbit a star. No one in that hall asked whether the universe might contain objects that satisfied every physical condition of planehood. Mass, shape, dynamical history, but had no stellar address. Planet formation does not consult human definitions. A planet forms when enough material in a disk accumulates under gravity to produce a body whose self-gravity dominates its shape. That disk usually encircles a young star, because stars condense from collapsing molecular cloud cores, and the angular momentum of the infalling gas naturally flattens it into a rotating plane. The disk is a byproduct of star formation, not a prerequisite for it. Disks can also form around brown dwarfs, objects below the threshold for hydrogen fusion. And theoretical models show that fragments of a molecular cloud can collapse directly into planetary mass bodies with no stellar nucleus at all. Even when a planet does form around a star, it is not guaranteed to stay. The gravitational dynamics of multi-planet systems are chaotic on timescales of hundreds of millions to billions of years. Planets tug on one another. Resonances lock and break. Orbits stretch and twist. A single close encounter between two gas giants can accelerate one of them past the escape velocity of the parent star. The planet is flung outward, ejected into interstellar space, carrying whatever moons and atmosphere it held on to. It becomes a world without a sun. None of this was unknown in 2006. The NICE model, published a year earlier by Gomes, Morbidelli, Leveson and Tsiganis, proposed that the early solar system had undergone a violent dynamical rearrangement in which the giant planets migrated to their current positions. The simulations showed that the process likely ejected one or more planets from our own system. The possibility that the galaxy was full of exiled worlds was already taking shape in the literature. The IAU's definition did not acknowledge it. Why does a definition matter? Because words gatekeep what we study, what we fund, what we name. The IAU's resolution demoted Pluto to a new category, dwarf planet, and in the same stroke rendered every free-floating planetary mass object in the galaxy officially not a planet. When the first unambiguous rogue planet was confirmed 7 years later, it had no taxonomic home. The discoverers called it a planetary mass object, or a free-floating planet, language that hedged against the 2006 ruling. The thing itself, 6 times the mass of Jupiter, glowing faintly at 80 light-years distance, had no star. By the letter of the law, it was not a planet. What else might be out there, drifting between the stars, denied a name because of a sentence drafted on a Thursday in Prague? What happens when the numbers start to add up? When every survey, every microlensing campaign, every deep field image suggests that the exiled worlds are not a handful, but a multitude? What happens when we realize that the definition of a planet, the category we built to contain everything from Mercury to Neptune, was written too small from the start? The physics has been waiting. A planet is what gravity makes. A planet is a mass threshold crossed, a shape pulled round, a history of accretion and collision and thermal evolution. Whether a star shines nearby is a matter of circumstance, not essence. The universe contains worlds that formed in the light and were thrown into darkness. It contains worlds that formed in darkness and never knew anything else. They exist. They are real. The question is not whether they are out there. The question is whether we are willing to see them. So how does a planet lose its star? The process is gravitational violence stretched across millions of years, and it has 2 distinct faces. The first pathway begins in the crowded nursery of a young planetary system. A new star ignites, and around it spins a disk of gas and dust, the leftover material from the cloud that collapsed to form the star. Inside this disk, planets grow. Dust grains stick together, forming pebbles. Pebbles coalesce into planetesimals, bodies kilometers across. Planetesimals collide and merge, building protoplanets. The largest sweep up gas directly from the disk, becoming gas giants. This is the standard formation story. It produces worlds in orbit around a star. For now, the problem is gravity. In a system with multiple large planets, every body pulls on every other body. The architecture that emerges from formation is rarely stable over the long term. Planets migrate. They drift inward through the disk, tugged by gas. They enter resonances with each other, orbits locking into integer ratios. Jupiter and Saturn, for instance, orbited the young Sun in a 3-2 resonance, Jupiter completing 3 laps for Saturn's 2. This arrangement amplified their gravitational influence until it destabilized the entire outer system. When resonances break, the result is catastrophic. One close encounter between 2 gas giants can transfer enormous orbital energy. One planet slows, sinking toward the star. The other accelerates. Its orbit stretches from a neat ellipse to a long trajectory that flings it outward. If the energy transfer is large enough, and simulations show it often is, the accelerated planet crosses the escape velocity of its parent star. The star that gave it birth cannot hold it. In a matter of thousands of years, the planet passes through the outer debris belt of its system and enters interstellar space. What happens on the planet during this ejection? Moons, if they exist, may be retained or stripped depending on their orbits and the violence of the event. Atmospheres around gas giants largely survive. The planet's internal heat, the residual warmth of its formation, accumulated over tens of millions of years, continues to radiate outward, cooling slowly. It leaves behind the disk of dust and gas that formed it. It leaves behind its sibling planets. It leaves behind the star whose light had fallen on its clouds for as long as those clouds had existed. The 2005 NICE model, named for the city where it was developed, reconstructed how this happened in our own system. Gomes, Morbidelli, Levison, and Tsiganis ran thousands of simulations of the early solar system. Their results showed that the four giant planets formed in a tighter configuration than they occupy today. The disk of planetesimals beyond Neptune, the precursor to the Kuiper belt, was more massive. As the giants interacted with this disk and with each other, their orbits shifted. Jupiter moved inward slightly. Saturn, Uranus, and Neptune moved outward. At a critical moment, Jupiter and Saturn crossed a 2-1 resonance, and the system underwent a chaotic disruption. The simulations produced the solar system we see. But they also produced something else. In a large fraction of the runs, a fifth giant planet was ejected. This world, an ice giant like Uranus or Neptune, was present in the early system but lost during the rearrangement. The gravity of the other giants, amplified by the resonance crossing, flung it into interstellar space. This is not a fringe result. It is a robust prediction of the model. Our solar system may have once contained at least 5 giant planets. We live around the 4 that stayed. The NICE model resolved a number of outstanding puzzles. It explained why the Kuiper belt is so sharply truncated at its outer edge. It explained the late heavy bombardment, a period roughly 4 billion years ago when the inner planets were pummeled by a surge of impacts. It explained the orbital eccentricities of the giant planets and the capture of Jupiter's Trojan asteroids. A fifth giant, ejected early, made everything else fit. We have not found it drifting in the dark. We almost certainly never will. But the physics says it is there. And if our system lost a planet, planetary ejection is not rare. Simulations of exoplanetary systems with varying architectures, different numbers of giant planets, different disk masses, different timescales, produce ejection fractions between 10 and 50%. In a system with 3 or more gas giants, the odds of at least one being expelled approach certainty. The process is part of the normal evolution of planetary systems. It is a feature, not a flaw. That is the first pathway. The second does not involve a star at all. In the vast molecular clouds where stars are born, gravity does not always produce a star. A cloud fragment collapsing under its own weight can form an object too small to ignite hydrogen fusion, a planet directly, without any stellar intermediary. This is not a planet that formed in a disk and was later ejected. This is a planet that formed like a star, through direct gravitational collapse of a gas clump, and simply lacked the mass to finish the job. The physics is star formation writ small. A region of a molecular cloud becomes denser than its surroundings. Gravity overcomes thermal pressure. The clump contracts, heats up at its core, and settles into a balance between gravity and internal pressure. If the mass of the fragment is below roughly 75 to 80 Jupiter masses, it cannot achieve the core temperatures needed for sustained hydrogen fusion. It becomes a brown dwarf, or, at the lowest end of the mass range, a planetary mass object. The boundary between a brown dwarf and a planet formed through direct collapse is fuzzy. Around 10 to 13 Jupiter masses for deuterium fusion. But objects below this threshold are planetary in all but their formation history. Directly coalesced planets carry a different chemical signature from ejected worlds. A planet that formed in a protoplanetary disk around a star incorporates heavy elements, carbon, oxygen, silicon, iron, that condensed out of the disk. The disk is enriched by the metals the star inherited from earlier generations of supernovae. An ejected planet carries this enrichment with it. Its spectrum, if we could measure it in sufficient detail, would show metal absorption lines comparable to its parent star. A planet formed through direct collapse is different. It condenses directly from molecular cloud material with a composition close to primordial hydrogen and helium. It is a nearly pure sample of the gas that filled the early universe. Its spectrum would be simpler, poorer in metals, closer to the abundance ratios of the Sun or a brown dwarf. It is a world without the chemical scaffolding that built Earth, Venus, or Mars. It is a star that stopped growing. Current observations cannot distinguish between these two pathways. Gravitational microlensing, the method that has found most rogue candidates, measures mass by the shape and duration of a brightening curve, but it does not reveal composition. Direct imaging can yield spectra if the object is warm and close enough, but the targets imaged so far are massive enough that the distinction remains ambiguous. The true origin ratio, how many rogue planets were ejected versus how many formed alone, is completely unconstrained. Why does the origin ratio matter? Because the mass distribution, composition, and prevalence of rogue planets all depend on which pathway dominates. Ejected planets sample the full range of masses produced by disk formation, from terrestrial bodies up to gas giants. Direct collapse objects are biased toward higher masses. A molecular cloud fragment smaller than roughly 1 Jupiter mass struggles to collapse, because thermal pressure resists gravity at those scales. If the rogue population is predominantly ejected, Earth mass wanderers could be common. If direct collapse dominates, the population may cut off around 1 Jupiter mass, and the galaxy's true planet-to-star ratio may be lower than current high-end estimates. The two pathways paint two different pictures. In one, stars are messy creators, building more worlds than they can hold, and the galaxy is littered with their cast-offs. In the other, the raw material of the cosmos occasionally produces a planet-sized object the way a river sometimes cuts a pool in the rock, by the simple, relentless action of physics on matter. Both pathways operate. Their relative contribution determines what is actually out there. So what happens after these worlds are alone? What does a starless planet look like? And could you ever stand on one? The answer begins with a telescope survey in 2013 that finally proved they were real. The starless planet question leads us soon to that orphan confirmed in 2013. But first, we have to reckon with our own backyard, with the possibility that our solar system is a crime scene, missing one of its own. The suspicion started not with a body found, but with evidence that something had to have been there. In 2005, 4 planetary scientists, Gomes, Morbidelli, Levinson, and Tsiganis, published a model that would reorganize our understanding of the solar system's youth. They worked in Nice, France. The model carries that name. It did not set out to find a lost planet. It set out to explain 3 awkward facts about the out-solar system that the standard formation story could not resolve. The first awkward fact is the Kuiper Belt. This ring of icy bodies beyond Neptune extends from roughly 30 to about 50 astronomical units from the Sun. At 50 astronewts, it stops sharply. The classical Kuiper Belt objects, those in nearly circular orbits, simply do not exist beyond that edge. There is no gradual fade. There is a wall. A smooth formation process would not produce a truncated disk. Something must have sculpted it from the outside. The second awkward fact is the late heavy bombardment. The Moon's surface carries a record of impact craters, and by dating the rocks returned by Apollo, scientists determined that a pulse of collisions hit the inner solar system roughly 3.9 billion years ago, 400 million years after the planets formed. Craters superimposed on craters show a spike in the impact rate that lasted perhaps 100 million years. Something had destabilized a reservoir of small bodies and sent them cascading inward. The third awkward fact is the orbits of the giant planets themselves. Jupiter, Saturn, Uranus, and Neptune do not circle the Sun in the neat, circular, evenly spaced arrangement that simple formation models predict. Their orbits carry small but measurable eccentricities. Jupiter's and Saturn's orbital periods are not in an exact resonance today, yet their present configurations suggests they passed through one in the past. The architecture of the outer system is not what you would get from a quiet, uneventful birth. The NICE model proposed a single dynamical story that explained all three facts at once. The four giant planets formed in a tighter configuration, spanning roughly 5 to 17 astronomical units, embedded in a massive disk of planetesimals extending beyond. Over hundreds of millions of years, gravitational interactions with the disk caused the planets to migrate. Jupiter moved inward a small amount. Saturn, Uranus, and Neptune moved outward. Then, at a specific moment, Jupiter and Saturn crossed a 2-1 orbital resonance, Saturn completing one orbit for every two of Jupiter's. What happened next was chaos. The resonance crossing amplified the gravitational kicks between the two largest planets. Their orbits became briefly eccentric, and their combined influence scattered Uranus and Neptune into the primordial planetesimal disk. The disk itself destabilized. Planetesimals flew in all directions. Some rained into the inner solar system, producing the late heavy bombardment. Others were ejected entirely. The outer edge of the disk was carved away, leaving the Kuiper belt truncated sharply at 50 Astungel-Utes. The giant planets, after the violence subsided, settled into their current, slightly eccentric orbits, with Jupiter's Trojan asteroids captured during the mayhem. The model was elegant. It unified multiple mysteries, but it produced something else every time the team ran the simulations. To match the final orbital architecture we observe, the initial configuration almost always required an extra giant planet. 5, not 4. This fifth giant, roughly the mass of Uranus or Neptune, was present in the early system. It orbited among the others, and during the resonance crossing, it drew a fatal gravitational encounter. In most of the simulation runs, upwards of 70%, depending on the exact initial conditions, the fifth planet was accelerated past escape velocity and flung into interstellar space. The planet was not destroyed, it was exiled. A world the size of Uranus or Neptune, formed around our Sun, kicked out by its own siblings before the Earth had finished cooling. Its departure solved the equations and left the 4 survivors we know. Consider what that means. Every diagram of the solar system you have ever seen, the neat concentric ellipses, the 8 familiar planets, the asteroid belt, is incomplete. It depicts the system after the crime. For the first few 100 million years of its existence, our solar system had at least 5 giant planets. The one that is missing was not small. It was roughly 15 times the mass of Earth. With a thick atmosphere of hydrogen and helium over an ice and rock core, it probably had a system of moons. It probably had rings. And then, in a span of a few million years, nothing in astronomical time, it was gone. No telescope will ever find it. It has drifted for more than 4 billion years, and the galaxy does not keep track of lost children. It is now tens of thousands of light years from the star that formed it, indistinguishable from the hundreds of billions of other rogue planets that fill the Milky Way. But the gravitational signature of its departure is still imprinted on the system it left behind. The Kuiper belt's abrupt outer edge is the scar. The late heavy bombardment is debris from the struggle. The eccentricities of the giant planets are remnant wobbles of a dynamical fight that lasted millions of years. Each of these lines of evidence points to the same event, a resonance-driven instability that reshaped the outer system and threw one member into the void. The NICE model's broad strokes are not controversial, though the exact timing of the instability is debated. What the model forced us to confront is uncomfortable. Our star could exile a planet. If ours could, every star could. The galaxy should be full of them, cold, dark, untethered, drifting between the points of light we can see. But for decades after that realization, there was no way to find even one. The problem was brutally simple. Planets do not shine. They reflect starlight. If a planet has no star, it emits almost nothing. Only the faintest trickle of heat left over from its formation, a glow that fades with every passing million years. An adult rogue planet, billions of years old, is as dark as the space it moves through. Catching one seemed impossible, an exercise in chasing shadows. Then a Polish astronomer named Bogdan Paczynski wrote a 3-page paper that changed everything. The year was 1986. Paczynski was at Princeton, and he was thinking about dark matter. Astronomers had long considered using gravitational lensing to find compact dark objects in the galactic halo. Stellar mass black holes, ancient white dwarfs, things that bend light but emit none. Paczynski argued that the same method could be aimed at the galactic bulge, where the density of background stars is highest. With patience, one might detect objects of much lower mass, not stars, not brown dwarfs, planets, free-floating planets. Gravitational lensing is Einstein's gift to those who search for the invisible. According to general relativity, mass curves, space and light follows that curve. When a massive object passes precisely between a distant background star and an observer on Earth, the object's gravity acts as a lens. It bends the star's light around itself, focusing it toward the observer. The star does not dim. It brightens in a symmetric achromatic curve, rising to a peak and falling away as the lens moves on. The signature is unmistakable. No astrophysical event looks quite like it. A flare, a variable star, a supernova, each has a tell. Microlensing is geometry. It is pure gravity, indifferent to the composition of the lens. What Paczynski realized is that a free-floating planet would produce a lensing signal with a specific character. No companion star would leave its mark on the light curve. The brightening would be a single, smooth, symmetric bump lasting a time determined entirely by the planet's mass and the relative motion of the lens and source across our line of sight. A star-sized lens might amplify a background star for weeks. A Jupiter-mass planet would do it in a day or two. An Earth-mass planet would take only hours. Perhaps less than an hour. The smaller the planet, the briefer the flicker. Catching such an event required a new kind of observation. The lensing probability is low. At any given moment, about 1 in a million stars in the Milky Way's bulge is being significantly lensed. To find a single event, you must monitor millions of stars continuously, night after night, for years. You must measure tiny variations in brightness across vast stellar fields and trigger follow-up observations within minutes when an anomaly appears, because planetary mass events are gone almost as soon as they begin. In 1986, this was science fiction, but by the early 2000s, survey teams in New Zealand, Chile and elsewhere were already operating wide-field cameras on modest telescopes, hunting for microlensing toward the galactic bulge. Initially, their targets were not rogue planets. They were looking for exoplanets bound to stars, detectable by a secondary bump in the light curve when the planet's own lensing added a brief spike to the star's main signal. The surveys were called OGLE, the Optical Gravitational Lensing Experiment, and MOA, Microlensing Observations in Astrophysics. They found planets, but they also generated a background noise of single-lens events. Brightenings with no companion signature, some of them extremely short. In 2011, the MOA collaboration announced an event that stopped conversations. The designation was MOA 2011 BLG 262. The light curve was a textbook symmetric bump, lasting less than 2 days. That duration pointed to a planetary-mass object. The probability that the lens was a star was effectively zero. The event was too short. The problem was that two interpretations fit the data equally well. In the first, the lens was a free-floating planet, somewhere between 3 and 10 Jupiter masses, drifting alone in the galactic bulge. In the second, the lens was a smaller planet, roughly half a Jupiter mass. orbiting a distant, unseen M-dwarf star, with the star itself contributing no detectable lensing signal. The geometry worked either way. The data could not distinguish. The MOA team reported a candidate free-floating planet, but they could not claim certainty. The results sat in the literature as a tantalizing maybe, a ghost that had whispered through the light but refused to be named. One candidate, ambiguous. Despite the theoretical certainty that rogue planets should exist, no single event had yet forced the confrontation. The search needed a detection that left no room for a hidden host star, an object seen directly, glowing faintly from its own formation heat, or a lensing event so short that the mass precluded anything other than a solitary world. Until that arrived, the rogue planet remained a logical necessity, not yet a confirmed population. The night was holding its secrets. What would it take to break the silence? What kind of instrument, what kind of patience, what kind of luck would catch a world that emits no light and vanishes in an hour? In 2013, something gave way. The search had been running for years. Microlensing surveys had produced one ambiguous candidate after another, hints that dissolved under scrutiny. The Nice model insisted the galaxy must be full of exiled worlds. The physics demanded them. But the telescopes had not yet forced the issue. Every signal could be explained away. A hidden star, a chance alignment, an instrument artifact. The rogue planet remained a theoretical certainty and an observational ghost. Then a survey that was never designed to find planets found one. Pan-STARRS 1 sits on the summit of Haleakala on Maui. It is not a planet hunter. It was built to scan the entire visible sky repeatedly, night after night, looking for asteroids and comets that might threaten Earth. A 1.8-meter telescope paired with a 1.4 billion pixel camera, the largest digital camera ever constructed, when it began operations in 2010. Every clear night, it photographs the sky in 5 color filters, building a time-lapse record of everything that moves or changes brightness. The data pipeline compares tonight's image to the archive and flags anything that was not there before or has moved since the last observation. In 2013, one of those flagged objects refused to behave. The first image was unremarkable, a faint red smudge in the constellation Dorado. The pipeline tagged it because it had moved slightly against the fixed background stars, the way a nearby asteroid moves. But the follow-up images did not show an asteroid's rapid trajectory. The object was moving too slowly, the parallax too small. It was not inside the solar system. It was far beyond, drifting at a distance measured at roughly 80 light-years. The team took a spectrum. What came back was strange. The object was cool, roughly 1100 Kelvin, around 800 degrees Celsius, still radiating heat from its formation. Its spectral type was L7, placing it at the boundary between star and planet. But there was no star anywhere near it. Deep searches in multiple wavelengths, including infrared surveys sensitive enough to detect brown dwarfs at much greater distances, found nothing. The object was alone, utterly alone. The designation was PSOJ 318.522. Its mass is about 6 times that of Jupiter. Its age, determined by its association with the Beta Pictoris moving group, a loose cluster of young stars born together about 12 million years ago, makes it an infant in astronomical terms. It still glows from the heat of its assembly, and it has no sun. The discovery team, led by Michael Liu of the University of Hawaii, published in October 2013. The paper was straightforward, a free-floating planetary mass object confirmed by direct imaging. No star within 1,000 astronomical units, no evidence of a binary companion. The object was not ambiguous like the microlensing candidates, not a maybe that could also be a distant, bound planet. It was there, in the image, a point of light with no larger light anywhere near it. the first unambiguous rogue. Philippe Delorme had glimpsed something similar a year earlier. In 2012, his team at the Institut de Planétologie et d'Astrophysique de Grenoble had been using the Canada-France-Hawaii telescope on Mauna Kea to search for brown dwarfs in Dorado. They found a faint, moving object, CFB-DSIR 2149-0403, roughly 4 to 7 Jupiter masses, also radiating formation heat. But its membership in a moving group was contested, and the evidence that it was truly free-floating was less clear-cut. It carried an asterisk. PSOJ 318.522 did not. The confirmation that rogue planets are real shifted the question from, do they exist, to how many, and what are they like? It opened a door that could not be shut. If POJ 318.522 is 6 times the mass of Jupiter and 80 light-years away, and we found it because it happens to be young and still warm, how many older, colder, darker ones drifted past unseen while we were looking at that same patch of sky? The microlensing surveys were already beginning to suggest an answer. In 2016, OGLE caught something smaller than anyone had anticipated. The optical gravitational lensing experiment has been scanning the galactic bulge from Las Campanas Observatory in Chile since the early 1990s. Its telescope is modest, 1.3 meters, but its reach into the dense star fields of the Milky Way's center is unmatched. By 2016, it had recorded thousands of microlensing events. Most were stellar lenses, the characteristic weeks-long brightening of a foreground star passing in front of a background one. But on a specific night, the survey recorded an event that lasted 41 minutes. Przemek Proz was the lead analyst. He worked at Warsaw University Observatory, where OGLE is headquartered. When the data pipeline flagged the event, designated OGLE 2016 BLG 1928, the duration alone told him it was unusual, 41 minutes. To lens a star for only 41 minutes, the lensing object had to be extremely small. Microlensing duration scales with the square root of the lens mass. A stellar mass lens produces a signal of weeks, a Jupiter mass lens a day or two. Something that flickers and vanishes in less than an hour points to a mass below Earth's, perhaps as low as Mars. Mroz and his team checked the light curve. It was a perfect symmetric bump, the fingerprint of gravitational lensing. No secondary spike from a companion star. No distortion from a binary lens. A single, compact, solitary mass had crossed the line of sight to a background star and bent its light. Then it was gone. The team ran the numbers. The most probable mass was between 0.3 and 2 Earth masses. The lensing in 2013, the automated pipeline flagged a faint, reddish point of light in the constellation Capricornus. It was moving, not fast enough to be an asteroid in our own solar system, but too fast to be a distant galaxy fixed in the cosmic background. The object was crossing the field at roughly 1/10 of an arcsecond per day. That motion placed it somewhere nearby in galactic terms, within a few dozen light-years. The question was what it orbited. The team searched the surrounding field for a parent star and found absolutely nothing. No stellar companion within tens of billions of kilometers. No gravitational tether visible in any wavelength. The object was alone. They gave it a catalogue designation, PSOJ 318.522. The name is clinical. The object was not. Follow-up spectroscopy from the NASA Infrared Telescope Facility and the Gemini North Telescope on Mauna Kea revealed what this thing actually was. The spectrum showed strong absorption bands of water vapor and methane, the unmistakable signature of a cool substellar atmosphere. The spectral type came back as L7. In the classification system for brown dwarfs and giant planets, L-type objects have surface temperatures between roughly 1,300 and 2,000 Kelvin. PSOJ 318.522 was sitting near the bottom of that range, around 1200 Kelvin, still glowing faintly from the heat of its formation. The spectrum also revealed a low surface gravity. The absorption lines were broader than they should be for an old, compact brown dwarf. This object was young, still settling, still radiating the residual energy of its birth. The mass estimate came in at roughly 6 times Jupiter. The age, determined by comparing its luminosity and temperature to models of planetary cooling, pointed to roughly 12 million years. A newborn by cosmic standards. The same age as a nearby group of young stars called the Beta Pictoris moving group, a loose association of stars that formed together and are still drifting through the galaxy in a common direction. PSOJ 318.5-22 appeared to be a member of this group, traveling with the same velocity through space. 80 light-years from Earth, 6 times the mass of Jupiter, 12 million years old. No star. This was not a candidate. It was not an ambiguous microlensing light curve that could be interpreted 2 ways. It was a directly imaged, spectroscopically confirmed, planetary mass object floating freely through interstellar space. The first unambiguous rogue planet ever discovered. The detective work that led to this moment had been building for years. In 2012, a team led by Philippe Delorme at the Institut de Planétologie et d'Astrophysique de Grenoble had announced the discovery of a similar object using the Canada-France-Hawaii telescope. That object carried the designation CFB Sire 2149-0403. It was roughly 4 to 7 Jupiter masses, also young, also glowing at around 400 degrees Celsius from formation heat, also apparently unattached to any star. Delorme's team believed it belonged to the AB Doradus moving group, another young stellar association about 100 million years old. But the association was debated. The object's proper motion placed it near the moving group, but not certainly within it. If the group membership was wrong, then the age was wrong, and if the age was wrong, the mass was uncertain. The object could be a very low-mass brown dwarf rather than a planet. The results stood in the literature as a probable rogue planet, but the uncertainty left a crack that skeptics could slip through. Delorme himself described the experience of finding it. Standing in the control room at Mauna Kea, watching the faint point of light drift slowly across successive images, verifying that no star lay within arc-minutes of its position. He told a reporter later that season that it was like seeing a ghost you had only heard rumors about. The shape was there, the presence was real, but you could not quite be sure what you were looking at. PSO J318.522 closed the crack. The Pan-STARRS 1 detection was cleaner. The object's membership in the Beta Pictoris moving group was more secure than CFB-DSR 2149's association with AB Doradus. The Beta Pictoris group is younger, only about 20 million years old, which meant PSOJ 318.5-22 was younger too. And for a given luminosity, a younger object must be less massive. A cooling planet fades with time. To be as bright as PSOJ 318.522 appeared, at an age of only 12 to 20 million years, the mass could not exceed roughly 6 Jupiters. That placed it firmly in the planetary mass regime, well below the deuterium burning limit of roughly 13 Jupiter masses that separates planets from brown dwarfs. No ambiguity remained. The object was a planet, and it was alone. The team published in the Astrophysical Journal Letters in October 2013. The lead author was Michael Liu of the University of Hawaii's Institute for Astronomy. The paper was direct. It stated that PSOJ 318.522 possessed all the spectral characteristics of a young, low-gravity, planetary mass object and had no detectable host star. The evidence for free float was not statistical. It was not inferred from the shape of a light curve. It was observed, directly. The implications rippled through the community. Until that moment, Rogue planets had been a prediction, a ghost story, a logical consequence of dynamical simulations that felt true but could not be verified. Now they were a fact. The galaxy contained worlds with no sun. What did it look like, this orphan? The spectrum gives some answers. At 1200 Kelvin, PSOJ 318.522 is still hot enough to glow a dull red in the near-infrared. If you could see it with eyes sensitive to those wavelengths, it would appear as a faint ember, cooling slowly. Its atmosphere is dominated by molecular hydrogen, with clouds of iron and silicate dust condensing at different altitudes, just as they do in the atmospheres of young brown dwarfs and directly imaged exoplanets. The surface gravity is low, about 1/3 that of a typical brown dwarf of the same temperature, which means the atmosphere is puffed up, extended, still settling under its own weight. It is a world in its adolescence, glowing with the last heat of its formation, drifting through the constellation Capricornus at a distance of 80 light-years. Consider that distance, 80 light-years. In the galactic neighborhood, this is close. The nearest star to Earth is just over 4 light-years away. The nearest known exoplanet orbits Proxima Centauri at roughly the same distance. PSO J318.522 is closer to us than most of the stars you can see with the naked eye. It is passing through our local spiral arm right now, and until 2013, no one knew it existed. It had no sun to illuminate it. It had no orbit to trace against a stellar disk. It had no gravitational footprint on any star within reach. It had been crossing the darkness silently for 12 million years, and it would have crossed it forever unseen if a telescope designed to find asteroids had not caught its faint thermal glow in a routine survey exposure. The discovery rewired the expectations. If one rogue planet this massive and this young could be found within 80 light-years by a survey that was not even looking for planets, then how many more must there be? The population estimates that theorists had been producing for years. The 200 billion rogue planets, the trillions, suddenly felt less like extrapolation and more like undercount. PSOJ 318.522 was not hiding. It was nearby. It was bright enough to be seen by a modest survey telescope. The fact that it existed at this distance, at this mass, implied a vast underlying population of fainter, older, smaller objects that current instruments could not touch. A single unambiguous detection. That was all it took to transform the rogue planet from a theoretical curiosity into an observational reality. And yet, PSO J318.522 was massive. 6 Jupiters, a gas giant, glowing in the infrared from its own residual heat. It was proof that free-floating planets existed, but it was not the proof that Earth-mass rogues were out there. For that, the search would need to push to the very edge of what physics allowed. It would need to catch something much smaller, much fainter, something that produced no glow and passed across a background star in less than an hour. What kind of instrument could catch a shadow that brief? To catch something that small, you need a different kind of eye. The OGLE survey had been watching the galactic bulge for years. The optical gravitational lensing experiment, based at Warsaw University Observatory, operates a 1.3-meter telescope at Las Campanas Observatory in Chile. Its sole purpose is to stare at dense star fields and wait for gravity to bend light. Every clear night, it photographs millions of stars in the direction of the Milky Way's core, where the density of background sources is highest and the chance of a lensing alignment is greatest. The survey has discovered thousands of microlensing events since it began in 1992. Planets orbiting stars, brown dwarfs, stellar mass black holes. Each event is a needle pulled from an ocean of data, and the needles keep getting smaller. On June 21, 2020, the pipeline caught something that almost slipped through. The event received the designation OGLE 2016 BLG 1928. The 2016 in the name indicates it was found in data from the 2016 observing season. It had been sitting in the archive for nearly 4 years before the analysis team, led by Przemek Mroz, identified it as something extraordinary. The delay tells you how subtle the signal was. This was not a bright, dramatic brightening that stood out in real time. It was a faint, fleeting blip buried in the noise of tens of thousands of stars, visible only after the most sensitive algorithms had combed through the full dataset. The light curve lasted 41 minutes. 41 minutes. That is the shortest microlensing event ever attributed to a planetary mass object. For comparison, typical stellar microlensing events last weeks or months. Even the shortest planet hosting star events span several days because the mass of the lensing object determines the duration. More mass means a wider Einstein ring, the distorted region of space-time around the lens, and a longer crossing time for the background star. Less mass shrinks the ring, shrinks the duration, shrinks everything about the signal. The shape of the light curve was textbook perfect. A smooth, symmetric rise to a single peak, followed by an equally smooth and symmetric decline. No secondary bump, no asymmetry, no telltale signature of a stellar companion anywhere in the system. The background star brightened, peaked, and faded in a clean bell curve that matched the Pachinski model exactly. The lens was a single, compact mass passing between the star and the telescope. The duration pinned the mass. Mroz and his team ran the calculations. For a lensing object in the galactic bulge, at distances typical for these events, a 41-minute timescale corresponded to a mass between Earth and Mars. The uncertainty spanned roughly a factor of 2 in either direction, but the central estimate placed it firmly in the terrestrial regime. This was not a gas giant. It was not a Neptune. It was a rocky or icy body, roughly the size and mass of our own world, give or take. No star accompanied it. The light curve showed zero evidence of a binary lens. If a host star had been present, its gravity would have distorted the microlensing signal, producing a caustic crossing, an asymmetric peak, or a secondary magnification feature. The data contained none of those. The lens was alone. The team estimated the distance. The most probable location placed the object roughly 20,000 light-years away, in the dense star fields of the inner Milky Way. At that distance, the signal was not just short, it was vanishingly faint. The magnification reached only a few percent above background, barely above the detection threshold, even for an instrument as sensitive as OGLE IV. Had the alignment been slightly less perfect, had the background star been slightly dimmer, had the telescope been pointed a fraction of a degree elsewhere, the event would have been invisible. Mroz described the experience later with an image that captured the absurd precision of the observation. Catching this signal, he said, felt like catching a falling leaf in a hurricane. The leaf was there, it was real, but everything around it was chaos, noise, the turbulence of a billion stars packed into a narrow field of view, each one flickering with its own variability, its own instrumental artifacts, its own statistical dance. And in the middle of all of that, for less than 3/4 of an hour, one star bent around one invisible planet, and the survey recorded it. The implication was immediate and severe. OGLE 2016 BLG 1928 represented the first credible detection of a terrestrial mass rogue planet. All previous microlensing candidates had been Jupiter mass or larger, the kind of worlds that could plausibly form through direct gravitational collapse as well as through ejection. This object was different. At Earth to Mars mass, it was too small to have formed like a star. Direct collapse from a molecular cloud fragment requires a minimum mass of roughly 1 Jupiter. Below that threshold, The fragment cannot cool and contract efficiently enough to become a self-gravitating object without accreting onto something larger. An Earth-mass body cannot form in isolation from a gas cloud. It must form in a disk, which means it must have been ejected. OGLE 2016 BLG 1928 was not merely a rogue planet. It was an exile, a world that had been born around a star, and then flung into the void by the same gravitational chaos that shaped our own solar system. This single detection proved that ejection operates down to terrestrial masses. It confirmed what the NICE model had implied for the outer solar system, but could never prove directly, because the ejected planet, if it existed, was long gone. Here was the same process, caught in the act. Not in our system, but in some other system billions of years ago, in the crowded inner galaxy. The statistics were thin. One event does not make a population, but one event proves the category exists, and the existence of the category forces the population estimates to adjust. If Earth-mass rogues can be detected at all, given the extreme difficulty of the observation, then they must be extraordinarily numerous. The telescopes are catching only the tiniest fraction of the total. Mroz and his collaborators calculated that the detection of even one such event implied a population of terrestrial mass rogue planets in the Milky Way numbering in the tens of billions or more. The exact figure depended on assumptions about the mass function and the spatial distribution, but the lower bound was staggering. The paper appeared in the Astrophysical Journal Letters in October 2020. The title was direct: A terrestrial mass rogue planet candidate, detected in the shortest timescale microlensing event. The astronomy community absorbed it with a mixture of excitement and unease. Excitement because the detection confirmed a long-standing prediction. Unease because it made the planet counting problem much harder. If Earth-mass rogues are common, then the total planetary population of the galaxy is dominated by objects that emit no light, reflect no starlight, and can only be detected through a gravitational alignment that lasts less than an hour. What does a world like this actually feel like? The mass estimate places it somewhere between Earth and Mars. If it is rocky, it has a solid surface. Mountains, valleys. Perhaps the remnants of ancient tectonic activity, frozen in place since the heat of its formation bled away into space billions of years ago. It has no atmosphere thick enough to retain warmth, because at this mass, any primordial hydrogen envelope would have escaped long ago. The surface temperature sits within a few degrees of absolute zero. The only heat comes from the slow decay of radioactive isotopes in the core, and that heat never reaches the surface. It stays buried under kilometers of frozen rock and ice, a whisper of warmth in a body that has known nothing but cold for most of cosmic history. It drifts. It has no orbit, no year, no seasons, no day-night cycle. The sky is exactly the same at every moment. The same stars, fixed in the same positions, slowly shifting over tens of thousands of years as the planet crosses the galaxy. The Milky Way stretches across the darkness like a faint, frozen river of light. And that is all. No sun, no moon, no dawn. OGLE 2016 BLG 1928 is not unique. It is the first of its kind to be caught, but it cannot be the only one. The physics of planetary formation guarantees that for every world like this detected, millions more pass through the galaxy unseen, their existence as real as our own and as invisible as a shadow crossing a shadow. How many millions? The answer was already waiting in a room in Boston, on a slide that stopped a conference cold. The American Astronomical Society meeting was already running late. Boston, January 2011. A grey winter afternoon outside the conference centre, the kind where the sky and the streets dissolve into a single, indifferent cold. Inside, hundreds of astronomers sat in a windowless hall, cycling through the final slides of the afternoon session. The coffee had gone cold. The chairs were hard. The attention in the room was thinning like a nebula at its edges. Then Wenjin Huang stood up. He was a researcher at the University of Washington. He had been running simulations that combined Kepler Space Telescope data with dynamical models of planetary system formation. The Kepler mission, launched in 2009, had been designed to find planets around other stars by watching for the tiny dips in brightness when a planet transited its host. Huang's question was different. He was not trying to count the planets that stayed. He was trying to count the ones that did not. He advanced to a particular slide. The projector flickered. The screen showed a black square of space, a patch of sky near the constellation Cygnus, dense with the pinprick light of distant stars. At first glance, it looked like any other deep-field image. The audience saw what they expected to see. Then their eyes registered the single red dot. One dot, bright and piercing against the black, Huang explained, in a quiet voice that cut through the ambient fatigue. That the red dot represented the estimate of how many planets in that field had been ejected from their birth systems. Not one or two, not a statistical error bar, an entire population. He had rendered them as a single point because the number was so large that drawing them individually would have filled the frame with solid red. The dot was not a planet. The dot was a census. The hall fell silent, the kind of silence where people stop breathing. The kind where you can hear the air conditioning and the creak of a chair and the distant rumble of an escalator in the lobby. Everyone in that room knew what they were seeing. A quiet graduate student from Seattle had just shown them a slide that implied the galaxy was fundamentally misclassified. The stars were not the central population. They were the minority. Huang gave voice to what the red dot meant. There are more of these exiled worlds than there are stars in our galaxy, he said. They are not rare. They are the majority. We just haven't opened our eyes to them. The words hung in the air. They landed with the weight of a paradigm shift that arrives without warning. The astronomers in the hall understood the physics immediately. They had known for years that planetary systems eject worlds. They had read the nice model papers in 2005 that suggested the solar system once had 5 giant planets and lost one. They had seen the microlensing hints, the ambiguous signals, the theoretical papers predicting a background of free-floating planets. But seeing it reduced to a single red dot on a single slide, a single census of a single field, transformed abstraction into shock. The simulation had used Kepler's sensitivity limits to estimate how many planets form per star and then applied gravitational scattering models to compute the fraction that get ejected. Huang's group calculated that the Milky Way could contain roughly 200 billion rogue planets. Not total, just Jupiter mass and larger. The number came from an independent path. It did not rely on microlensing. It came from the statistics of bound planets and the inevitable chaos of their interactions. The implications of the simulation aligned with a growing body of evidence. That same year, a team led by Takahiro Sumi of Osaka University published a paper in Nature that analyzed 2 years of microlensing data from the MOA survey. MOA, Microlensing Observations in Astrophysics, used a 1.8-meter telescope at New Zealand's Mount John Observatory to monitor 50 million stars in the galactic bulge. Sumi and his collaborators searched the light curves for the characteristic signature of gravitational lensing and found 10 events that lasted less than 2 days each. The events were too short and too symmetric to be lensing caused by stars. There were no secondary signatures, no binary caustics, no evidence of a host star anywhere near the lens. The interpretation was stark. The lenses were Jupiter mass objects, free-floating in the galaxy, crossing in front of background stars, and producing fleeting glints of magnification. The rate of these events implied a number. Sumi et al. Calculated that there are roughly 2 Jupiter-mass rogue planets for every main sequence star in the Milky Way. With approximately 100 billion stars in the galaxy, the arithmetic was direct. 200 billion Jupiters adrift. No sun, no orbit, no category that the IAU's 2006 definition could accommodate. 200 billion. The number is too large for the human mind to inhabit. We can recite it. We can write it on a blackboard. We can compare it to grains of sand on every beach on Earth and find it greater. But we cannot feel it. The mind is built for herds of a few dozen, forests of a few thousand, skies of a few thousand visible stars. 200 billion is not a quantity. It is a category error. And the 200 billion were only the ones the surveys could detect. Huang's slide suggested something larger still. His simulations included planets of all masses, not just the gas giants that dominate microlensing sensitivity. The ejection process does not discriminate by mass with clean selectivity. Lower mass planets scatter more easily in some dynamical configurations. Earths and super-Earths, Neptunes and sub-Neptunes, worlds made of rock and ice and iron, all get thrown into the void with the same gravitational indifference. Huang's group estimated that the total population across all masses could be 5 to 50 times larger than the Jupiter mass count. The slide stayed on the screen for a long moment. Not because Huang was pausing for effect, because the room was not ready to move on. The red dot burned against the black field, a single pixel encoding a truth that rewrote the galaxy, and no one wanted to look away from it. Later attendees described the silence as physical, a pressure in the chest, the sound of several hundred people recalibrating their understanding of the universe simultaneously. One astronomer, unnamed in the conference reports, told a colleague in the hallway afterward that he had felt, for the first time in his career, like a child who had been told the ocean is not the water but the creatures inside it. The paradigm shift was not only in the numbers. It was in the realization that the discoverers themselves were being changed by what they found. Philippe Delorme felt it in the fall of 2012. He was leading a team at the Institut de Planétologie et d'Astrophysique de Grenoble, using the Canada-France-wide telescope on Mauna Kea. The telescope's 3.6-meter mirror was trained on the constellation Dorado, scanning for brown dwarfs. These are objects that blur the boundary between planet and star, massive enough to fuse deuterium but not hydrogen, glowing faintly in the infrared from the heat of their formation. Delorme expected to find brown dwarfs. He found something else, a faint point of light, moving slowly against the fixed background of distant stars over several nights of observation. Its temperature registered at roughly 400 degrees Celsius, far too cool for a star, too cool even for most brown dwarfs. But the object was young, still radiating the retained heat of its assembly, and it was alone. No parent star within billions of kilometers. No gravitational tether to any luminous body. Delorme and his team checked and rechecked. They traced its proper motion through the AB Doradus moving group, a loose association of young stars drifting together through the galaxy. The object's mass fell between 4 and 7 Jupiters. It had the temperature of a planetary body, the mass of a planetary body, the spectrum of a planetary body, and it orbited nothing. They named it CFB Tsar 2149-0403, the first candidate free-floating planet detected by direct imaging. And when Delorme spoke to the press, he did not reach for the clinical language of a discovery paper. He said, "It was like finding a planet that had been thrown out of its home. But we had no idea where the home was. It was completely alone." He would later add a line that no telescope can capture, but every astronomer understands. Like seeing a ghost you've only heard rumors about. The metaphor was precise. For decades, theorists had predicted these worlds would exist. The NICE model had argued the solar system itself ejected at least one. Paczynski had built the mathematical framework to detect them in 1986. Simulations had churned out estimates of their population. But no one had ever seen one. The ghost was a rumor, a whisper in equations, a shadow in the statistics. Then Delorme's telescope caught it in the infrared, a faint ember drifting through Dorado, 80 light-years from Earth, with no star to call its own. 8 years later, and halfway around the world, another astronomer caught another ghost. This one was not infrared. It was gravitational. Przemek Mroz was working with the OGLE collaboration, the optical gravitational lensing experiment, based at Warsaw University Observatory. OGLE had been watching the galactic bulge for decades, monitoring hundreds of millions of stars, waiting for the telltale brightening that signals a massive object passing in front of a background light source. On June 21, 2020, the system flagged an event. A star in the dense fields near the galactic center had brightened and dimmed in a curve that was smooth, symmetric, and complete. No wobble, no secondary peak, no sign of a companion lensing the star simultaneously. Just a single, clean arc of magnification lasting 41 minutes. The team ran the models. The mass needed to produce that curve was not Jupiter's, it was not Saturn's. It was between the mass of Earth and the mass of Mars, an object smaller than any planet ever detected outside the solar system, moving through interstellar space with no star, bending the light of a distant sun for less than an hour before vanishing into darkness again forever. Mroz described the feeling later with an image that has become the signature of the terrestrial mass rogue era, catching a falling leaf in a hurricane. Think about what that sentence means operationally. OGLE watches millions of stars. A microlensing event by a stellar mass object can last weeks or months. The signal is strong, the duration is generous, the detection is statistically manageable. But an Earth mass rogue produces a signal that rises and falls in less than an hour. The alignment must be nearly perfect. The background star must be bright enough, the lens close enough, the geometry exact enough that the tiny gravitational deflection registers above the noise floor of a telescope on the surface of Earth. Looking through atmosphere, looking through dust, looking through the 1,000 other sources of variation that plague every observation. And yet the signal was there. Clean, unmistakable, a falling leaf, caught. The moon is not what you think it is. For 53 years, since the last Apollo astronaut left its surface in 1972, we convinced ourselves we understood it. A dead rock, a grey companion, geologically quiet and fully mapped. Then on April 6, 2026, 4 astronauts aboard the Orion spacecraft swung around its far side, the half that permanently faces away from Earth. And what they found there shattered that comfortable illusion in a matter of hours. Their names are Reed Wiseman, Victor Glover, Christina Cook, and Jeremy Hansen. They are the crew of Artemis II, and the first time a woman, a black astronaut, and a non-American have ever ventured beyond Earth orbit. They launched from Kennedy Space Center at 6:35 in the evening on April 1st, 2026, riding atop the most powerful rocket NASA has ever built, the Space Launch System. The SLS stands 322 feet tall and generates 8.8 million pounds of thrust at liftoff. It took them out of Earth orbit in a single burn that lasted less than 5 minutes. From that moment, there was no turning back. The trajectory they followed is called a free return, meaning that even if the spacecraft's engine had failed completely after that burn, the moon's gravity would have slung them around and sent them falling back toward Earth on its own. Apollo 13 followed the same kind of trajectory in 1970. It is the safest path to the moon, which also tells you something about how dangerous this still is. The safest option is the one that accounts for total engine failure. As they passed behind the moon at roughly 4,600 miles above its surface, they became the most isolated humans who have ever lived. For 40 minutes, the moon itself blocked every radio signal between their spacecraft and Earth. No voice from Houston, no telemetry, no abort commands, nothing but silence. And the oldest, most battered landscape in the solar system stretching out beneath them. Victor Glover, the mission's pilot, tried to describe what he was seeing in real time to mission control before the blackout hit. He couldn't. Not really. His exact words radioed down during the flyby were that humans probably have not evolved to see what they were seeing, that it was truly hard to describe. And when the signal cut out at 6:44 in the evening, Eastern Time, the four of them were alone with it. So, what did they see? To understand why the far side of the moon is so disturbing, you first need to understand how different it is from the side we see every night. The near side, the one that faces Earth, is covered in vast dark plains called Maria. Ancient lava flows that filled enormous craters and cooled into flat basalt seas billions of years ago. About 31% of the near side is covered in this volcanic rock. It gives the moon its familiar face, the one we've drawn and photographed and painted for centuries. The far side has almost none of it, less than 1%. Instead of smooth plains, the far side is a wall of craters stacked on top of craters, stacked on top of older craters, a landscape so saturated with impacts that every new crater obliterates a dozen older ones. The surface looks pulverized, churned, wrong. The astronauts described it not as a landscape, but as a violence preserved in stone. Something fundamental happened differently on the two sides of the moon. Two worlds fused into one sphere, and we still do not fully understand why. That night in April, 4 people saw it with their own eyes. By the time their signal returned to Earth, the mission had already changed. Not the mission parameters, what we thought we would find. Now shift your attention outward, past the moon, past Mars, past the asteroid belt, past Jupiter, whose magnetic field screamed radiation warnings at every probe we ever sent, past Saturn's rings, out where the sun is no longer the dominant presence in the sky. 2 machines are still traveling there. They left Earth in the late 1970s with a mission that almost no one expected them to complete. They were supposed to see Jupiter and Saturn, maybe a few moons, maybe last 5 years. Instead, they are still alive. Voyager 1 and Voyager 2 have been flying for more than 4.5 decades, and they are still sending back data that changes the textbooks. What they taught us was that the universe is not a series of stable systems. It is a place where objects get thrown out. The same gravitational interactions that shaped our solar system, the slow dance of Jupiter and Saturn migrating through their orbits, the jostling of Uranus and Neptune, the scattering of comets into the deep freeze of the Oort cloud, these same forces, given slightly different starting conditions, can accelerate a planet to escape velocity and fling it into the void. And if our own planetary system ejected bodies, then every system does. The question is not whether there are planets floating alone in the dark. The question is how many. Every planet humans have ever seen orbits a star. That statement held true for the entire history of astronomy until the 21st century. Every world directly observed, every body imaged by spacecraft, every exoplanet detected by the Kepler telescope or the radial velocity surveys, all of them orbit a sun. The connection between planets and stars appears absolute in the data. It is not. It is a sampling bias. Planets close to stars are easy to find. They transit, they tug, they reflect light. A planet without a star is a planet hiding in the one place telescopes cannot illuminate. Everywhere. The physics of planet formation never required a star. A planet forms when material in a disk accumulates under its own gravity into a body massive enough for self-gravity to dominate its shape. That disk typically forms around a star because stars form from collapsing molecular cloud cores, and angular momentum naturally produces a disk. But the same physics operates around brown dwarfs, objects below the stellar mass threshold. And under some conditions, a molecular cloud fragment can collapse directly into a planetary mass object without any stellar nucleus at all. No star, no disk, just gravity pulling gas together until it becomes a world. Even planets that do form around stars have no guarantee of staying. The gravitational dynamics of a young planetary system are chaotic on timescales of millions to billions of years. The same forces that sculpted the architecture of our own solar system, the same migration and resonance and close encounters, can fling planets clean out of the system entirely. The physics is blunt. If two gas giants pass close enough, one gains energy, the other loses it. The loser spirals inward, the winner accelerates outward. If the kick exceeds the escape velocity of the parent star, the planet leaves. It does not return, it becomes a rogue. In 2005, a team of researchers published a model that rewrote the early history of our solar system. The Nice model, named for the city in France where it was developed, proposed that Jupiter, Saturn, Uranus, and Neptune did not form where they are now. They formed in a more compact configuration, then migrated outward through a period of dynamical instability. The gravitational chaos of that migration scattered smaller bodies everywhere. It may also have done something else. The model suggests our solar system once had a fifth giant planet, an ice giant similar to Uranus or Neptune in mass, orbiting among the other four. During the instability, that fifth giant encountered Jupiter or Saturn at the wrong angle, at the wrong distance, and the encounter launched it out of the solar system entirely. We cannot prove this. The planet is gone. If it exists, it is somewhere in the galaxy now, drifting, cold, undetectable, a ghost of our own past. This is not a fringe idea. The paper was published by some of the most respected dynamicists in the field. The model reproduces the current orbits of the giant planets and the distribution of small bodies better than any alternative that does not include an ejection. Our solar system may be a crime scene, and the crime was the exile of a world we will never see. Now scale that process up. The Milky Way contains roughly 100 billion stars. Most of those stars formed with protoplanetary disks. Most of those disks produced multiple planets. A significant fraction of those planets, perhaps 10 to 50%, experienced gravitational encounters violent enough to eject them. The arithmetic is not complicated. Multiply 100 billion stars by an average of a few ejected planets per system, and the number of rogue planets in our galaxy alone enters the hundreds of billions. Some models push it into the trillions. The high estimates make rogue planets the most common type of planet in the universe. The worlds that orbit stars become the exception. The worlds that drift alone become the rule. But a number on a page is not a detection. To find these objects, astronomers needed a method that did not depend on light. They needed a way to see gravity. In 1986, a Polish astronomer named Bogdan Paczynski published a paper that proposed something audacious. He suggested that if a massive, dark object passed directly between a background star and a telescope on Earth, its gravity would bend and magnify the star's light in a characteristic symmetrical curve. The effect is called gravitational microlensing. The object itself emits nothing. It can be as dark as the space around it. But its mass warps the fabric of space-time, and that warp becomes a lens. The star brightens. then dims. The shape of the light curve reveals the mass of the lens. For a rogue planet, Paczynski predicted, the event would be extraordinarily brief, minutes to hours, and it would lack any secondary signal from a host star. A lone object, a clean, single peak, a shadow moving across the galaxy, visible only because it bent the light of something far behind it. The prediction was elegant. The detection was almost impossible. To catch a microlensing event, you must monitor millions of stars continuously, waiting for one of them to brighten by a fraction of a percent for a few hours, then fade back to normal. You must distinguish that signal from stellar variability, from instrumental noise, from the 1,000 other things that make stars flicker. And for a rogue planet, you get one chance. The alignment is random. The object passes. The event ends. It will never repeat. If you blink, you miss it. The first credible candidate came in 2011. The Microlensing Observations in Astrophysics Collaboration, MOA, detected an event called MOA 2T111 BLG262. The light curve suggested a free-floating planetary-mass object. But the data was ambiguous. The signal could have been a planet unbound from its star, or it could have been a planet at a wide separation from a star too faint to see. The team could not rule out either interpretation. It was a hint, not a proof. The proof arrived the following year, from a different method entirely. Direct imaging. A team led by Philippe Delorme of the Institut de Planétologie et d'Astrophysique de Grenoble was using the Canada-France-Hawaii telescope on Mauna Kea in Hawaii to search for brown dwarfs in the constellation Dorado. They pointed the telescope at a patch of sky and took images separated by months. They were looking for faint objects that moved. Stars are too distant to show motion over human timescales. Objects in our own solar system move too fast. But something in between, a planetary mass body drifting relatively nearby, would shift slowly against the fixed background. Delorme's team found one. The object was designated CFB-DSR 21490403. Its temperature was measured at roughly 400 degrees Celsius, still glowing faintly from the heat of its formation. Its mass was estimated between 4 and 7 times that of Jupiter. It belonged to the AB Doradus moving group, a loose association of young stars that formed together roughly 120 million years ago. But the object had no star, no companion visible at any wavelength. Delorme's own words captured the feeling of that moment. It was like finding a planet that had been thrown out of its home, but we had no idea where the home was. It was completely alone. He later described the discovery as seeing a ghost you have only heard rumors about. That phrase is precise. The object was not a rumor anymore. It was a point of light on a detector. But it was also a ghost in the original sense. A presence whose origin was unknown. A body that should not have been alone, yet was. In 2013, the Pan-STARRS 1 survey in Hawaii found a second one, PSO J318.522. This time, there was no ambiguity. The object was roughly 6 times the mass of Jupiter. Its surface temperature was about 800 degrees Celsius. Its spectral type was L7, classifying it as a cool substellar object with clouds of molten iron and silicate dust in its atmosphere. And it had no parent star, none. The surveys were deep enough to rule out a stellar companion of any type brighter than the dimmest brown dwarfs. PSO J318.522 was alone, 80 light-years from Earth, drifting through interstellar space with nothing to orbit and nothing orbiting it. This was the first unambiguous rogue planet. Not a candidate, not a maybe. A world adrift, confirmed by direct imaging. The proof that Delorme's ghost and the microlensing hints were not anomalies. The galaxy really did contain planets without stars. The question shifted from whether they exist to how many exist. And the answers that came next were staggering. At the 2011 American Astronomical Society meeting in Boston, a researcher named Wen-Jin Huang from the University of Washington stood up to present a set of simulations. Huang had used data from the Kepler Space Telescope, which had been staring at a single patch of sky cataloguing exoplanets, and extrapolated the ejection rates from the architectures of systems Kepler had found. The models estimated how many planets are thrown out of their birth systems during the chaotic early phases of planet formation. The numbers were not modest. Huang projected a slide. It showed a patch of black space. In the center was a single red dot. The implication was unavoidable. Kepler had mapped the planets that survived. The ejected ones, the ones that did not survive, outnumbered them. The slide hit the room like a physical object. The audience stopped breathing. Huang's own words carried the weight of the calculation. There are more of these exiled worlds than there are stars in our galaxy. They are not rare. They are the majority. We just have not opened our eyes to them. The microlensing surveys kept running. They had to. An event lasting less than an hour on a random star in one of the densest fields in the sky is as close to impossible as observational astronomy gets. Przemek Mroz, a researcher at Warsaw University Observatory working with the OGLE collaboration, spent years sifting through data in which almost everything was noise and almost nothing was a planet. On June 21, 2020, he and his team announced a detection. The event was designated OGLE 2016 BLG 1928. The year reflects when the data was collected, not when the analysis was finished. The 4-year gap between observation and publication is its own measure of the difficulty. The team had to rule out every alternative explanation. Instrumental artifact, a variable star mimicking the signal, a background binary eclipsing at the wrong moment. They eliminated everyone. What remained was a microlensing event lasting 41 minutes. The star brightened and dimmed in a perfect symmetrical curve, the unmistakable fingerprint of a compact mass passing in front of it. No secondary peak, no wobble, no host star. The duration told them the mass. A lens moving through the galaxy at typical stellar velocities, producing an event that brief had to be tiny on astronomical scales. The best estimate placed it between the mass of Earth and the mass of Mars. This was not a gas giant. This was a rocky world, or something close to it, drifting alone somewhere near the galactic bulge, 20,000 light-years from the telescope that caught its shadow. Mroz described what it felt like to catch such a signal. He compared it to catching a falling leaf in a hurricane. The comparison holds. The signal was faint. It was fast. It could have been anything. And it passed through the telescope's field of view exactly once, never to repeat. If the survey had been looking somewhere else that night, if the weather had been bad, if the data processing pipeline had rejected the event as noise, the planet would still be there, invisible, unknown, crossing the void without a witness. The detection changed something fundamental. Klaczynski's method, proposed as a theoretical exercise in 1986, had now progressed from ambiguous candidates to the unambiguous detection of a terrestrial mass object. The ghost had a mass. The rumor had a weight. The red dot in Huang's slide had been caught in the act of bending light. Didier Queloz watched these discoveries accumulate from a position of singular authority. In 1995, he had co-discovered 51 Pegasi b, the first exoplanet orbiting a Sun-like star. The discovery had inaugurated the modern era of planet hunting. It won him the 2019 Nobel Prize in Physics. Queloz had built his career finding planets around stars. But by 2021, walking through a corridor at Cambridge University, gesturing with the energy of someone who has seen a door swing open that no one else has noticed, he was talking about planets without any star at all. In an interview with the Royal Astronomical Society, Queloz called rogue planets the next frontier in astrobiology. The phrase was deliberate. He did not say they harbor life, he said they change the story. Every assumption in the search for extraterrestrial biology had been built around the presence of a sun. The habitable zone, the orbital band where surface water stays liquid, the energy budget of photosynthesis, the day-night cycle, the seasons, all of it assumed a star as the central engine of any biosphere. But if a planet could sustain subsurface oceans through the decay of radioactive isotopes, through tidal heating from a retained moon, through the insulating blanket of a thick hydrogen atmosphere, then the star was optional. The engine could be internal. Queloz's exact words landed in the conversation the field had been having, but no one had yet stated plainly. "We always thought life needs a sun," he said. "But these planets may have internal heat from radioactive decay and tidal forces. It changes the story completely. The darkness is not empty. It may be full of possibilities." That sentence. The darkness is not empty. Spoken not by a science fiction writer, not by a journalist chasing a headline, but by a Nobel laureate who had spent his career building the catalogue of worlds around distant suns. The admission contained its own quiet revolution. The search for life had been for decades a search for light. Now, the man who helped find the first exoplanet around a sun-like star was saying in public that the real frontier might be the place no telescope can directly illuminate. The pattern across these four voices does not repeat. It accumulates. Huang's red dot in Boston forced astronomers to confront the census. The galaxy contains more exiled worlds than stars. Delorme's ghost in Dorado gave the census a face. A real object, a point of light on a detector, not a statistical inference. Rosa's falling leaf in the galactic bulge proved the census included worlds the size of our own. Terrestrial mass bodies, rocky or icy, drifting alone in numbers no one had dared to estimate. And Queloz's statement at Cambridge extended the consequence beyond astronomy into biology. The census was not merely a curiosity. It was a challenge to every assumption about where life can exist. Each move shifts the story further from the old certainty and closer to a universe where darkness is not the absence of something. It is the presence of something we are only beginning to name. The emotional register of these discoveries is not what textbooks would lead you to expect. Science is supposed to be dispassionate. Confirmations of theory, gradual refinements. But the discoverers of rogue planets do not sound like people confirming a prediction. They sound like people who have touched a new category of existence and are still processing what it means. Delorme's press statement carried an undertone of disbelief, the kind that comes when you find something you were taught could not exist. Mroz's hurricane metaphor came from a mind trained to expect failure, confronting success so unlikely it feels like a gift. Huang's silent slide stopped a room full of experts from breathing. Queloz's excited gesticulation in a Cambridge corridor betrays a realization that has not yet cooled into textbook prose. The ghost is not a rumor. The leaf has been caught. The red dot has been counted. The frontier has been named. What remains is the question Queloz left hanging in that corridor, the one that pulls the entire enterprise forward into the dark. If the darkness is not empty, what is waiting out there for us to find? You want to know what it feels like, not what the telescopes see, not what the equations predict, what it feels like to stand on one. In 2019, Scientific American published an article that contained no new data, no detection announcement, no mass estimate. It contained a single paragraph written by an astronomer who chose to remain unnamed, and that paragraph has since been passed between researchers like something private that accidentally became public. The astronomer was asked to imagine the surface of a rogue planet. Not to model it, not to simulate it, to stand on it. The description begins with what is missing. No sun rises, no sunsets. There is no dawn to wait for, no dusk to measure the passage of time. The sky does not change color because the sky has no color. It is black. Not the black of a moonless night on Earth, which is really a deep blue scattered through atmosphere and dust. This is a black so complete it feels solid. A black that presses against the eyes like velvet. A black that has not been interrupted by a photon of direct starlight since the planet was ejected from its birth system or collapsed into existence from a fragment of molecular cloud. The Milky Way is there, but barely. A faint, ghostly band smeared across the dome of the sky, so dim that after a few minutes of looking, the eyes begin to doubt whether they are seeing it at all, or inventing it to fill the void. No individual star is bright enough to resolve. The galaxy is not a spray of lights. It is a suggestion of texture in an otherwise featureless dark. The astronomer's exact words were these: no sun, no moon, no stars moving across the sky. Only the blackness and, if you are lucky, a faint glow from the Milky Way. But that too is almost dead. The sky is not a sky, it is just an abyss. Look down. The surface underfoot is ice, not the thin, temporary ice of a winter pond. Ice that has been frozen for billions of years. Ice that has never known liquid water at its surface. Ice that has accumulated every molecule of volatile material the planet ever possessed and locked it into a crystalline lattice, kept stable by cold that is almost absolute. The temperature at the surface of a typical Earth-mass rogue planet, far from any star and any source of external heat, settles to within a few degrees of absolute zero. 2.7 Kelvin is the background temperature of the universe, the faint afterglow of the Big Bang, and the surface of a rogue planet has no reason to be warmer than the space around it. The cold is not weather, it is a physical constant. Walk forward, the ice does not creak. It does not groan under the shift of weight. It is too cold for that. At these temperatures, water ice is harder than steel, a rigid crust that transmits vibration with the dead, unresonant character of a solid that has forgotten what movement feels like. Each footstep rings faintly through the ice, a brief, muffled percussion that travels outward into the dark and dies. There is no echo, there is nothing for sound to bounce off. Reach down, touch the surface. The cold is not a sensation so much as an amputation. It does not register as pain because the nerves stop signaling before pain can form. The moisture on the skin flash freezes. The ice adheres. That is a property of water at these temperatures. It welds to flesh. The hand must be pulled away quickly, or it will not be pulled away at all. The body radiates heat. On a rogue planet, the body is the hottest object for thousands of kilometers in any direction. Heat flows outward from the skin into the black sky with nothing to reflect it back. The sense of cold is not from the air, because there is almost no air. What thin atmosphere may exist, perhaps a wisp of hydrogen or helium retained by gravity, is so tenuous it cannot conduct meaningful heat. The cold comes from the loss of radiant energy into an infinite sink. Standing on this surface, a human being is a brief, impossible candle burning in a universe that has no use for light. No shadow stretches from the feet. On Earth, even on an overcast day, the diffusion of sunlight through clouds casts diffuse shadows, shapes that anchor the body to the ground. Here there is no light source to cast a shadow in any direction. The figure of the observer blends into the ice. The ice blends into the sky. The boundary between solid ground and infinite space becomes a guess. After enough time in this darkness, the brain begins to lose the distinction between self and surroundings. The proprioceptive sense, the quiet internal knowledge of where the body ends and the world begins, starts to fail. This is not metaphor. This is a documented response to sensory deprivation, and a rogue planet is the most complete sensory deprivation chamber in the universe. Standing there, it becomes possible to understand something the data alone cannot convey. These worlds are not dead because nothing lives on them. They are dead in a deeper sense. Nothing happens. The surface of a rogue planet is a place where time has stopped. The ice does not melt and refreeze. The crust does not shift. There is no weather, no erosion, no chemical cycle. The only change is the slow, steady loss of internal heat, radiating upward through kilometers of rock and ice, a flux so faint it cannot raise the surface temperature by a fraction of a degree. The planet cools, but it cools on geological timescales. 1,000,000 years passes without leaving a visible trace. And yet, beneath the ice, beneath the frozen crust, beneath the silence, the interior of the planet is not dead. Radioactive isotopes, the same potassium-40, thorium-232, and uranium-238 that keep Earth's mantle convecting and its core molten, decay on a rogue planet just as they decay everywhere else. The heat they release has nowhere to go except upward, through the rock, through the ice, into the abyss. But the conduction is slow. The heat is trapped. Kilometers beneath the frozen surface, the temperature may be warm enough for liquid water. Oceans sealed under ice shells thicker than anything in the solar system. Oceans that have never seen light. Oceans that may have been dark and liquid and chemically active for the entire history of the universe. Standing on the surface, none of this is visible. The abyss above, the ice below, the silence, the cold. The interior is a secret the surface keeps perfectly. The anonymous astronomer closed the description with a line that has since become a kind of koan among researchers who study these worlds. The sky is not a sky. It is just an abyss. Read it again and notice what it does not say. It does not say the sky is empty. It says the sky is something else entirely. An abyss is not a void. It is a depth whose bottom cannot be seen. A depth that implies something below. The galaxy is full of these surfaces. Trillions of them, if the higher population estimates are correct. Trillions of ice plains under trillions of black skies. Each one a separate universe of darkness and cold and crushing quiet. Each one a world where the boundary between surface and space has dissolved. Standing on one, it becomes impossible to see the others. The galaxy as a network of lights is an illusion of distance. Close up, the galaxy is a sea of isolated darkness, punctuated by brief, warm islands around stars. The space between those islands is populated by worlds that will never see a sunrise, worlds where time has no measure, worlds where the only light, the faint smear of the Milky Way, is itself a reminder of everything the planet cannot reach. What does it feel like to stand there? It feels like being inside the ghost, not watching it, not detecting it, being it, the cold, the silence, the sky that is not a sky, the faint, dying glow of the galaxy that cannot warm you, the knowledge that beneath your feet, sealed under ice that has not melted for 4 billion years, liquid water may be moving in the dark, and you will never know. The awareness that you are standing on a world that outnumbers every star, and no one is coming to find you. Now turn around. Look back at the sky. Somewhere in that faint band of light is a star with 8 planets. One of them has oceans on its surface, blue and open to the sun. One of them has life that evolved eyes to see the light and a mind to wonder about the dark. That world is the anomaly. You are standing on the norm. The darkness is not empty. It is full of worlds like this one. The question that remains is not whether they exist. It is what exists down inside them, where the ice meets the heat, where the silence meets the sea. What is waiting in the dark that we have not yet learned to see? The surface is frozen, but the interior tells a different story. To understand why, start not in interstellar space, but inside our own solar system, at Jupiter. The moon Europa has no sunlight reaching its subsurface. Its surface temperature averages minus 160 degrees Celsius. The ice shell is estimated at 15 to 25 kilometers thick. Below that shell, a global ocean of liquid water has been confirmed by magnetic field measurements from the Galileo spacecraft in the 1990s. The ocean is kept liquid by tidal heating, the gravitational flexing of Europa's interior as it orbits Jupiter in an eccentric path. Compress rock and it heats. Stretch it and it heats again. The physics is direct. The consequence is a saltwater ocean larger than all of Earth's oceans combined, sealed under ice, completely dark, and potentially habitable for 4 billion years. Europa does not orbit a rogue planet, but the mechanism that sustains its ocean does not require a star. It requires an energy source deep inside the world itself. You think you know what a planet is. A world orbiting a star, a bright point in a telescope, or a pale dot in the sky. That is what every planet ever seen, every world ever walked upon, every body whose surface has been mapped or sampled has been. Planets orbit stars. The association is complete and it is ancient. The International Astronomical Union, the global authority on astronomical nomenclature, embedded that assumption directly into the definition of a planet in 2006. The definition that demoted Pluto requires a planet to orbit the Sun, not a star. The Sun specifically. The definition does not merely assume a stellar host. It makes orbit around our own star the fundamental criterion. The physics has never required this. A planet forms when material in a disk accumulates under gravity into a body large enough for self-gravity to dominate its shape. That disk usually orbits a star because stars form from collapsing molecular cloud cores and angular momentum naturally creates a disk. But disks can form around brown dwarfs, and models show that gravitational instability in molecular clouds can collapse directly into planetary mass objects with no stellar nucleus involved. A star is convenient, it is common, it is not necessary. And even when a planet forms around a star, it is not guaranteed to stay. The gravitational dynamics of multi-planet systems are chaotic over cosmic timescales. The same interactions that shaped the architecture of the solar system can, under different initial conditions, fling one or more planets entirely out of the system. The association between planets and stars is empirical instruction, not a physical law. The universe contains planets without stars, billions of them, possibly trillions. And their existence forces a question that astronomy has been avoiding. What do you call a world that has everything a planet has except a sun? The answer, it turns out, is not in the definition. It is in the dark. The process of becoming free is violence at planetary scale. Rogue planets arrive at their unattached state through two distinct pathways, and the distinction matters because it controls mass, composition, and the odds of habitability. The first pathway is ejection. During the formation of a planetary system, gravitational interactions between forming planets, particularly gas giants, whose masses make them gravitationally dominant, can accelerate one or more planets past the escape velocity of the parent star. The whole system rearranges and one body loses. It is thrown outward at tens of kilometers per second, crossing the orbit of its outermost sibling in months, crossing the boundary of the stellar heliosphere in years, entering interstellar space with no possibility of return. The NICE model of solar system formation, published in 2005, proposes that the early solar system underwent exactly this kind of dynamical instability. Jupiter, Saturn, Uranus, and Neptune migrated to their current positions through gravitational interactions that rearranged the entire outer system. And in that rearrangement, a fifth giant planet, something with the mass of Neptune or greater, was ejected from the solar system entirely. We had 5 gas giants, we have 4. One is gone, thrown into the galaxy billions of years ago, now tens of thousands of light years away, drifted beyond any possibility of detection. The same process operates in planetary systems with different architectures, different numbers of giant planets, different disk masses, different timescales, and the result is the same. Planets are ejected. Simulations show that 10 to 50% of planets formed around stars may be lost during formation and evolution. Every bright, stable system you see in the night sky is the survivor of a gravitational war that killed off the losers by exile. The second pathway is stranger. A rogue planet need not form around a star at all. A molecular cloud fragment can collapse directly into a planetary-mass object without ever accreting onto a star or brown dwarf. The predicted mass range for this pathway is 1 to 10 Jupiter masses. These objects are born in darkness, never lit, never warmed by a stellar nursery. They are star-like in composition, hydrogen-helium dominated, and they blur the boundary between planet and failed star. Why the distinction matters. Ejected planets retain the heavy element enrichment of their parent star's protoplanetary disk. They have carbon and oxygen and nitrogen and iron in proportions that reflect their birth around a star. Direct collapse objects have primordial composition, closer to stellar abundance ratios. They are chemically different, structurally different, and the ratio between them tells us whether most rogue planets are exiles from stellar families or natives of the dark. Current observations can measure mass. They cannot measure composition. The ratio is unconstrained, but they are out there, both kinds. And the first step toward finding them was taken not with a telescope launch, but with a theoretical prediction made in the fading years of the Cold War. In 1986, the Polish astronomer Bogdan Paczynski proposed something that sounded like a magic trick. If a massive object passes precisely between a background star and an observer on Earth, the gravity of that object will bend the star's light like a lens. The star will brighten in a characteristic, symmetric curve and then dim again as the alignment passes. This is gravitational microlensing, and Paczynski realized it could detect things that emit no light of their own. Brown dwarfs, black holes, and free-floating planets. The catch is alignment. The object and the star and the Earth must line up to within a fraction of a milliarc second, a precision that makes threading a needle look clumsy. The probability of alignment for any given star and any given lens is astronomically low, which means you must monitor millions of stars simultaneously and continuously, waiting for one of them to brighten for a few minutes or a few hours as a dark body crosses the line of sight. The signal from a rogue planet is especially brief, minutes to hours. The light curve is perfect, symmetric, and there is no secondary signature from a host star because there is no host star. The theory was elegant. The implementation was brutal. Ground-based surveys like OGLE, the optical gravitational lensing experiment based at Warsaw University, and MOA, the microlensing observations in astrophysics collaboration, and KMTNet, the Korean microlensing telescope network, began staring at the dense star fields of the galactic bulge in the 1990s and 2000s. They detected microlensing events by the thousands. Most were star-on-star. A few in the data, a tiny fraction, showed the fingerprint of something planetary and alone. The first candidate came in 2011, MOA 2011 BLG 262, a microlensing event with the right shape, the right duration, but ambiguous. It could have been a free-floating planet. It could have been a planet on an extremely wide orbit around a star too faint to detect. The signal did not resolve the ambiguity. It was a hint, not a proof, and the field needed proof. It arrived in 2013 from a telescope called Pan-STARRS-1, the Panoramic Survey Telescope and Rapid Response System, perched on Haleakala in Hawaii. The object was PISO J318.522. It was not found by microlensing. Because it is young, only a few tens of millions of years old, and still hot from its formation, about 1200 Kelvin, it glows faintly in the infrared. Pan-STARRS 1 detected that glow directly, a moving point of heat with no parent star in its vicinity. The mass is approximately 6 Jupiter masses. The distance is roughly 80 light-years from Earth. Its spectral type is L7, a classification that places it in the temperature range of the coolest brown dwarfs and the hottest gas giants. It has every property of a massive planet, except one. It orbits nothing. It drifts through the AB Doradus moving group, a loose association of young stars, but it is not bound to any of them. It is alone. PSO J318.522 was the first unambiguous rogue planet, the one that converted the field from theoretical expectation to observational fact. Philippe Delorme, who discovered another rogue candidate called CFB-DIA 2149-0403 in 2012 using the Canada-France-Hawaii telescope, described the moment of recognition in terms that have stuck with the field. It was like finding a planet that had been thrown out of its home, but we had no idea where the home was. It was completely alone. Later, he added a line that captures the unease these objects produce. Like seeing a ghost you have only heard rumors about. The catalogue of rogues grew slowly, because the detection problem is monstrously difficult. A cold old rogue planet emits almost nothing. No visible light, negligible radio, infrared flux that falls below the noise floor of all but the most sensitive instruments. The only reliable method for the vast majority is microlensing, and the requirement for alignment means you must watch millions of stars for years to catch a handful of events. In 2020, the OGLE collaboration detected OGLE 2016 BLG 1928. The event lasted 41 minutes. The star brightened and dimmed in a perfect symmetric curve. The textbook signature of a lensing mass and the brevity and the absence of any companion signal indicated an object of roughly Earth to Mars mass crossing the line of sight at high speed. It was the smallest, lowest mass rogue ever detected, and its discovery meant that the population extended all the way down from superjupiters to terrestrial worlds. Przemysław Mroz, the lead author on the detection, described the effort required to catch such a signal. Catching it felt like catching a falling leaf in a hurricane. The turbulence he was referring to was not wind. It was the photometric noise of Earth's atmosphere, the constant shimmer that buries sub-percent brightness variations in a sea of random fluctuation. A 41-minute planetary microlensing event is a ripple on a ripple, and ground-based telescopes are staring up through an ocean of air to see it. They succeeded, and the success opened a question that the earlier, higher mass detections had only hinted at. How many of these things are out there? Wenjin Huang did the math. In 2011, at the American Astronomical Society meeting in Boston, Huang presented results from simulations that took the Kepler Space Telescope's exoplanet statistics and extrapolated them to the free-floating population. His model predicted that the Milky Way could contain approximately 200 billion rogue planets. 200 billion starless worlds, unattached, drifting through the disk and the halo, crossing the spaces between stars in numbers comparable to the stars themselves. Huang projected a slide showing an empty patch of black space with a single red dot. The room went silent. He told the audience, "There are more of these exiled worlds than there are stars in our galaxy. They are not rare. They are the majority. We just have not opened our eyes to them." The range in the population estimates is not a sign of confusion. It is a sign of how thoroughly our instruments were not built for this task. Microlensing surveys like the ones from Sumi and colleagues in 2011 produce an estimate of roughly 2 Jupiter-mass rogues per star, implying 200 billion in the galaxy. Theoretical simulations that account for ejection dynamics and low-mass planets produce numbers of 5 to 50 rogues per star, which pushes the total toward 5 trillion. Analysis by Gould and Mroz and other microlensing groups, using more conservative detection efficiency corrections, places the Jupiter mass rogue rate at 1/4 of a star each, bringing the number down to 25 billion. NASA and the Kavli Institute, in a 2023 synthesis, estimated that rogue planets outnumber stars by a factor of 20, which implies roughly 2 trillion total. That is a factor of 1,000 between the low and high estimates. It is not a rhetorical gap. It is a scientific controversy grounded in genuine uncertainty about the mass function, the efficiency of ejection, the nature of direct collapse, and the lower mass cutoff of the free-floating population. The high estimates assume the mass function rises steeply toward low masses, as it does for stars, meaning that for every Jupiter mass body, there are many more Earth mass and Mars mass bodies. The low estimates assume the mass function flattens or cuts off below roughly Neptune mass. The answer determines whether the galaxy is populated by a modest population of massive wanderers or a vast ocean of small, dark worlds. The problem is not that we lack models. The problem is that we lack data because Earth mass rogue planets are invisible to current instruments. The 41-minute event of OGLE 2016 BLG 1928 was an achievement, not a routine detection, and it represents the absolute lower limit of what ground-based microlensing can reach. Most Earth mass rogues pass unseen, their light curves buried in atmospheric noise, their alignments missed, because no telescope was watching that particular star at that particular moment. The data will come. A telescope designed specifically to solve this problem is in its final stages of assembly. But before we go there, before we reach the instrument that will count the uncountable, we must sit with a deeper implication. The definition of a planet is broken, and the breakage is not academic. It controls what we are allowed to name, and naming shapes attention, and attention shapes funding, and funding shapes what we discover next. The International Astronomical Union's definition, adopted in Prague in August 2006, is 9 words that exclude an entire class of worlds. A planet is a celestial body that is in orbit around the Sun. That clause, the first of 3, was written for the solar system. The object was to clean up the mess of Pluto and Eris and the growing list of Kuiper Belt objects that threatened to swell the planetary census. The solution was a definition that requires a planet to orbit the Sun, to have sufficient mass for hydrostatic equilibrium, meaning a nearly round shape, and to have cleared the neighborhood around its orbit. Pluto failed the 3rd criterion. It was demoted. The definition worked for what it was designed to do, but it was designed for 8 bodies in a single system, and it was never meant to encompass the galaxy. The IAU issued a working definition for exoplanets in 2003, before Prague, and updated it briefly afterward, but the 2 definitions are not fully consistent. A 13 Jupiter mass object orbiting another star is an exoplanet under the working definition. The same mass orbiting the Sun would not be a planet, because it exceeds the deuterium burning limit that the solar system definition implies, but does not state. The definitions are a patchwork, assembled at different times for different purposes, and they are cracking under the weight of new data. PSOJ 318.522 does not fit. It has 6 times the mass of Jupiter, a temperature of 1200 Kelvin, and a clear planetary mass formation history. It orbits nothing. Under the IAU definition, it is not a planet. It is not even a category. The discoverers called it a free-floating planetary mass object, a phrase that concedes the physical reality while respecting the definitional failure. Every paper on rogue planets uses similar workarounds. Planetary mass object, isolated planetary mass candidate, free-floating world. The language strains because the official language refuses to accommodate what the telescopes have already shown. The definition will change. The only question is when, and what we will call these things in the meantime, while the catalogues swell with objects that are planets in every respect except the one that a human committee in Prague thought was essential. In 2018, the IAU Commission on Exoplanets and the Solar System began informal discussions about revision. Nothing was adopted. Any change will be contentious. An intrinsic definition, one based on the physical properties of the object rather than its orbital relationship, would force the reinstatement of Pluto, would grant planetary status to dozens of Kuiper Belt objects, to the largest asteroids, to every free-floating body above the mass threshold. The number of planets in the solar system alone would jump to over 100. The true number in the galaxy would become uncountable. That prospect alarms some astronomers. An intrinsic definition, they argue, dilutes the category until the word planet loses all meaning. A planet is defined by its dynamical role, by its gravitational dominance of its orbital zone. Without that criterion, we lose the thread of what makes planetary systems structured and evolutionarily coherent. The opposing camp, which includes many of the researchers actually studying rogue planets, argues that nature does not care about human categories. A planet is an outcome of formation physics, not a relationship. Refusing to name what we are discovering is not rigor. It is avoidance. The debate is not settled, but the coming data will make it irrelevant. The Nancy Grace Roman Space Telescope, which will launch in 2026 or 2027, will detect hundreds of free-floating planetary mass objects. Some will be Jupiter mass, some Neptune mass, some Earth mass, some smaller. Each will be announced, catalogued and studied. Each will have a mass, a trajectory through the galaxy, a formation history, possibly a moon. They will have no stellar host. They will emit no light of their own. They will drift between the spiral arms of the Milky Way in perfect darkness. And the astronomers who study them will use the word planet because it fits. The only entity that will refuse to use that word is a sentence drafted 2 decades earlier by a body that was not thinking about interstellar wanderers. The sentence will become obsolete. It already is. The Roman Space Telescope is a $3.9 billion observatory named for the woman who convinced NASA that the Hubble Space Telescope was worth building when Congress wanted to kill the program. Nancy Grace Roman was the agency's first chief astronomer. She fought for Hubble in the 1970s, when it was a troubled budget line with a long development timeline and uncertain returns. She died in 2018, before the telescope that now bears her name took physical form. But its mission is her intellectual heir. Hubble showed us what the universe looks like. Roman will show us what it contains. Launch is scheduled for the window between October 2026 and May 2027. Roman will ride a Falcon Heavy into an orbit around the Sun-Earth L2 Lagrange point, a stable gravitational basin 1.5 million kilometers from Earth in the anti-sunward direction. From that perch, with Earth and Moon and Sun all behind its shield, it will stare into darkness with a wide-field instrument, a camera that captures a field of view 100 times larger than Hubble's at the same resolution. A single Roman image will cover the equivalent area of a full moon, but with the depth and sharpness of a space telescope, unblurred by atmosphere. That field size is not a luxury. It is the hard requirement for catching rogue planets. by microlensing. To detect a 41-minute brightening of a star, you must monitor millions of stars continuously for years, because the alignment is rare, the signal is brief, and it never repeats. Ground-based surveys have been doing this for decades. OGLE and KMT-net and MOA stare at the galactic bulge, where the density of background stars is highest and the odds of alignment are greatest. They detect roughly 2,000 microlensing events per year, nearly all of them star-on-star. The rogue planet events, the ones with no stellar companion in the lens, the ones that rise and fall in under an hour and vanish, are a tiny fraction buried in noise. Roman survey is designed to catch them. The telescope will stare at the same fields in the bulge every 15 minutes, around the clock, for months at a time. The cadence is fast enough that a 41-minute microlensing spike, which a ground-based telescope might catch as a single anomalous data point between clouds, will be captured in multiple consecutive images, confirming the light curve and pinning down the mass of the lensing object in real time. The sensitivity extends downward into territory that has been entirely dark to us. Roman will detect rogue planets down to the mass of Mars, not Jupiter mass orphans, of which we have a handful, not Neptune mass candidates, of which we have a few tentative signals, but Mars mass bodies, objects smaller than Earth, objects whose gravitational signature on background starlight is so small that no current instrument can register it. The telescope's position above the atmosphere eliminates the photometric shimmer that buries these tiny signals for ground-based surveys. A brightness fluctuation of less than 1%, lasting 40 minutes, will be measurable. The predicted yield changes the field from discovery to census. The catalogue of unambiguous rogue planets currently fits on 2 hands. PSOJ 318.522, the OGLE detections, a few microlensing candidates still under analysis. That is the total direct evidence for a population that, by the most conservative estimates, numbers in the billions. Roman is expected to detect not dozens but hundreds of free-floating planetary mass objects during its microlensing survey alone. The exact number depends on the mass function, the lower cutoff, the true abundance, which is precisely what the survey will determine. But the projections, published in peer-reviewed mission planning documents, place the expected haul in the range of several hundred to over 1,000. Every one of those detections will be a mass measurement, not an upper limit, not a rough estimate with factor of 3 uncertainty. A mass derived from the duration and amplification of the light curve, pinned down by a space telescope with continuous coverage and precise photometry. The distribution of masses, how many are Jupiter mass, how many are Neptune mass, how many are Earth mass or smaller, will emerge from that data not as a theoretical extrapolation, but as a direct sampling of the population. The billion versus trillion controversy does not survive Roman's primary mission. The factor of 1,000 gap between the low and high estimates is not a philosophical disagreement. It is ignorance about the low mass end of the mass function. Sumi and colleagues in 2011 inferred roughly 2 Jupiter mass rogues per star from a sample bias toward massive objects. Huang's simulations, extrapolating from Kepler data and theoretical mass functions, produced numbers in the hundreds of billions and higher. Neither number is wrong. Both are extrapolations from different assumptions about what the distribution looks like below the detection threshold. Roman erases that threshold. The telescope will measure the mass function of free-floating planets across at least 2 orders of magnitude in mass, from roughly Jupiter down to Mars. The shape of that function, whether it rises steeply toward lower masses, flat lines, or peaks at some intermediate value, will answer the origin question that the entire field has been circling since Pachinski proposed microlensing for planet detection. If the mass function rises toward low masses, the ejected planet pathway dominates, because planetary system dynamics fling small bodies more efficiently than large ones. If the mass function cuts off below roughly Neptune mass, the direct collapse pathway gains primacy, because molecular cloud fragmentation has a natural lower limit. The data will decide. Roman also maps the positions and distances of the detected rogues across the galactic bulge constrain the spatial distribution. Are they concentrated in the galactic plane, like stars, implying a formation origin in the disk? Do they follow a spherical halo distribution, hinting at an older, primordial population ejected early in galactic history? Each detection comes with a line of sight location, and with enough of them, a three-dimensional picture of the invisible galaxy begins to resolve. The telescope exists. It is not a concept or a proposal working through committees. The Wide Field Instrument completed its final cryogenic vacuum tests at Goddard Space Flight Center in 2024. The coronagraph instrument, which will demonstrate direct imaging of exoplanets from space, has undergone its own test campaign. The spacecraft bus is being integrated. It is hardware in clean rooms, awaiting a ride to orbit. When it begins operations, Roman will not look at rogue planets directly. It will look at stars, millions of them, and wait for the light from one of those stars to bend around a dark body drifting across the line of sight. The planet will remain invisible. Only the warped space around it will register, a momentary brightening that reveals mass, distance, and velocity. The object that caused it will pass unseen, in the dark, as it has for billions of years. We will not see these worlds. We will count them by their shadows in space-time. And when the survey is complete, we will know whether our galaxy contains more starless worlds than stars, how small the typical rogue is, whether a planet like Earth, suddenly ejected into the interstellar dark, is a cosmic freak or a common occurrence. We will know the shape of the hidden galaxy, and that knowledge will arrive not as a theoretical inference, but as a catalogue, with masses, with positions, with light curves, archived for anyone to examine. What was invisible becomes counted. What was unknown becomes a field of study. Roman is not designed to end a debate. It is designed to replace the debate with data. And the data is coming. The lit world is not the norm. It is the exception. Earth bathes in the light of a star, and for 4 billion years life has organized itself around that radiance, building photon capture machinery in every leaf and every microscopic alga, timing its rhythms to sunrise and sunset, to season and solar cycle. We assumed, and it was a rational assumption given the evidence available, that this arrangement was the template. Planets orbit stars. Life requires stellar energy. The search for habitable worlds meant the search for surfaces illuminated by the right kind of star at the right distance. The rogue planet dismantles that assumption, not by disproving it, by making it insufficient. Once we know, and we now know, with the force of confirmed detection and rigorous theory, that planetary mass bodies exist without stellar hosts in numbers that likely exceed every star in the Milky Way, the equation flips. The question is no longer whether a few lost worlds might harbor some marginal, frozen ecology. The question is whether lit planets are the unusual ones, the rare bright islands in a galaxy of drifters that do not need a sun to call themselves alive. The mathematics of the inversion are stark and growing starker. Conservative microlensing estimates put Jupiter mass rogues at 1/4 of a star each. Less conservative estimates, grounded in the same data but making different assumptions about the low mass end, push the total into the trillions. Roman will close that gap But even the lower bound, 25 billion free-floating planetary mass objects in the Milky Way, already dwarfs the number of stars. And those are the detectable ones. The Earth mass and Mars mass bodies are almost certainly more numerous, following the same mass function logic that makes small stars more abundant than large ones. If a fraction of those worlds retain internal heat sufficient for liquid water, then the number of potentially habitable environments in this galaxy does not merely exceed the number of stars. It exceeds the number of star-warmed habitable zones by orders of magnitude. 10 billion star-warmed planets in the galaxy, as a generous upper bound drawn from Kepler's statistics. Against a trillion rogues, even if 1 in 10,000 retains a habitable subsurface ocean, the dark worlds win. Not by a margin, by a landslide. The physics that makes this plausible is not speculative. It is the same physics that keeps Europa's ocean liquid beneath an ice shell kilometers thick, 480 million miles from the sun. Europa has negligible solar energy. What it has is tidal heating. The gravitational kneading from Jupiter and the other Galilean moons, that flexes the satellite's interior and converts mechanical stress into heat. That heat maintains a global ocean of liquid water, possibly more water than all of Earth's oceans combined, sealed beneath ice, beneath vacuum, beneath the cold of the outer solar system. A rogue planet ejected with its moon intact, and models suggest many ejected planets would retain their moons because the ejection impulse acts on the system as a whole, carries its own Europa with it into the dark. The star is gone, but the tidal flexing continues. The moon orbits the planet. The planet's gravity pulls the moon into a slight eccentricity. The varying tidal stress warms the interior, and that ocean persists. A planet of several Earth masses, with a large moon in a close orbit, could sustain significant tidal heating for billions of years after ejection. The sun was never essential. Gravity was. And tidal heating is only one pathway. Radiogenic heating, the slow decay of potassium-40, thorium-232 and uranium-238 in a planet's mantle and core, produces roughly 4 terawatts of heat inside an Earth mass body. That heat leaks outward, maintaining geothermal gradients, driving volcanism, and, if the planet's crust and any overlying ice or atmosphere provide enough insulation, sustaining liquid water deep underground. A hydrogen atmosphere thick enough to trap that heat, and hydrogen is a greenhouse gas of impressive opacity, could extend the liquid water window from the subsurface all the way to the surface. A rogue planet with a dense hydrogen envelope, a mass above roughly 1/10 of Earth's, and enough water inventory could maintain a liquid surface ocean for the entire main sequence lifetime of a typical star. 10 billion years of liquid water, floating in darkness, powered by the slow death of unstable atoms in its own core. The habitable epoch of a rogue planet is not a brief flash. It is longer than the habitable epoch of Earth has been so far. And it is independent of stellar evolution. A rogue planet does not care when the galaxy's star formation rate peaks. It does not care when its parent star swells into a red giant and incinerates everything in the inner system. It is self-sufficient. It drifts while stars ignite and burn and die, and its ocean stays warm. This changes the geography of life. The search for biosignatures has been a search for transiting planets in stellar habitable zones, for atmospheric spectra showing oxygen and water vapor against the background glare of a sun. That search is valid, and it will continue, and it will find what it can find. But it is looking in a subset. The lit subset, the illuminated minority of habitable real estate that happens to be near a star, the kind of planet that is easiest to detect and most familiar to imagine. The dark majority remains invisible to transit spectroscopy, invisible to direct imaging at the flux levels we can measure, and unrepresented in the catalogues of potentially habitable worlds that drive target selection for missions like the James Webb Space Telescope. Earth is not representative. It is a brightly lit exception to the rule that most abodes for life in this galaxy are dark, enclosed, heated from within, silent in the frequencies we monitor. The silence between stars is not emptiness. That is the realization the rogue planet forces, and it is not a metaphor. Every volume of interstellar space we have called void is transited by bodies. They are invisible because they emit no light of their own and reflect none. They are dark in the visible, dark in the infrared, below the sensitivity of all but the most targeted surveys, dark in the radio. Their presence is registered only by the bending of background starlight, a signal so rare and so brief that a planet can cross 1,000,000 light-years before it aligns precisely enough with a star and a telescope to be detected. But the fact that a thing is invisible does not mean it is absent. The galaxy contains a hidden population of worlds that slip between the stars like fish in a lightless ocean, and the total surface area of those worlds, the total volume of liquid water they contain, the total inventory of organic chemistry they carry, exceeds the corresponding inventory of the lit, visible stellar entourage planets that have occupied our attention since the first exoplanet was Confirma. Our own exile from that darkness is the anomaly. Earth was born close to a star and has stayed there. But the word exile implies banishment, and in the cosmic sense, the banishment worked the other way. We are the ones cut off from the majority condition, trapped in a narrow, hot, radiation-flooded band around a nuclear furnace, while most worlds drift in the cool, calm, steady darkness, where the only light is the diffuse glow of the Milky Way itself. A faint band of unresolved stars that casts no shadows and provides no warmth. A civilization that evolved on a rogue planet's moon, around a subsurface hydrothermal vent beneath kilometers of ice and hydrogen, would have no concept of a sun. Its astronomers, finally breaking through the ice shell after millennia of effort, would emerge into a universe of unrelieved blackness, cold pinpoints of distant stars, the soft smear of the galactic plane. And they would conclude, perhaps, that they were lucky to live on a world that had everything it needed inside it, and that the bright, burning things in the sky were the exceptions. Dangerous, unstable, short-lived. They would be right. The astrophysicists and biologists who have begun thinking seriously about rogue planet habitability include Didier Queloz, the co-discoverer of the first